Hello, myself Dr. VJD Kalyani, working as Associate Professor in the Department of Computer Science and Engineering of Institute of Aeronautical Engineering. In this video, I will discuss about binary division algorithm. At the end of this video, the student will gain knowledge regarding what is binary division process, how the hardware can be supported to implement the binary division, what are the types of binary division, and the flowchart with examples can learn about the binary division. The basic agenda of this video is the introduction, examples, hardware implementation, flowchart, and decimal arithmetic unit. So here the binary division is a little bit complicated when compared to the addition and subtraction algorithms. Division of two fixed point binary numbers in signed magnitude representation is carried out with a successive comparison and shift operation and subtract operations. So the comparison, shift operation and subtract operations are majorly involved in the binary division. And also division is a simple and straightforward method. The objective of the division is to divide the dividend by a divisor and to obtain the quotient and remainder. What is the binary division process? The number of bits taken at the first instance equal that of the bits in the divisor. These bits are considered from MSB onwards. The comparison can be taken place by comparing the divisor with the dividend value and what exactly the divisor bits are there. The number of bits from the dividend starting from MSB are considered. This set of bits from the dividend are compared with the divisor. If dividend set is greater than the divisor, a 1 is placed in the quotient, else a 0 is placed in the quotient. The partial remainder at this stage is derived by the subtraction of the divisor from the dividend set of bits. The next most significant bit from the divisor is appended to the partial remainder. The divisor is shifted right. Steps 2 to 4 are repeated until the bits in dividend are used up. So here how exactly the decimal division can be performed. Similar way here the binary division can also be performed. The binary division is very simple when compared to the decimal division. Here the comparison can be done, only two digits are available in the binary, either 0 or 1. By taking from the MSB, if MSB contains a 1 higher order bits, then the number can be treated as the greater. Comparison can be simple, and here if it all 1, the divisor can be copied, and if it all 0, the number of 0 bits equal to the number of bits of divisor can be copied, and subtraction operation can be performed in order to get the partial remainder. So consider an example. One dividend is 0,111 and the dividend is divisor is this. So the divisor consists of 5 bits. So from the MSB of the dividend we have to consider in the divisor the 5 bits. So this is the 1, 2, 3, 4, 5 bits. Until this we have to take the divisor bits and you must make a comparison that whether the dividend is greater or the divisor is greater. So if you take here the MSB bit of the divisor can be the 1. So here, but here if you compare it should be 0. So the divisor can be less than, the dividend 5 bits can be less than the divisor. So we have to consider the next bit. So in the dividend, the 6 bits can be considered. So until this we have to consider, and we can make a comparison whether the dividend is greater or divisor is greater. So when taken up the sixth bit, the dividend can be greater. So we have to write a 1 at the exactly the sixth bit position, and we must copy the divisor here. Why? Because we written 1. So we have to copy the divisor here. After copying the divisor, we must perform the subtraction. So 0 minus 1, 1 with a borrow 1, 0 minus 1, 1 with a borrow 1, 1 minus 1, 0, 1 minus 0, 1, and these 2 bits can be 0. So we have to take these 4 bits and append the next bit of the dividend. So these 5 bits can be considered and a comparison can be made. And here if you compare that, 3 ones are available in the dividend. So here in the second position, third position and the fifth position ones are available, but in the divisor only in the first position and fifth position. So the dividend can be greater. And we have to write a 1 here and copy the divisor value. And again perform the subtraction. So the division can be a sequence of successive comparisons, subtraction and shifting operations. So here 0 minus 1, 1 with a borrow 1, 1 minus 1, 0, 1 minus 0, 1, remaining all are zeros. Next we have to append the next bit of the dividend. So if you look into the divisor, the dividend can be less than the divisor value. So we have to keep a 0 here and get down this 0. Now if you compare here, the dividend value can be greater. So 1 can be written here and copy the divisor here. Again perform the subtraction. So 0 minus 1, 1 with a borrow 1, 0 minus 1, 1 with a borrow 1, 1 minus 1, 0, 0, 0. Remaining all are zeros. Next we have to append the last 0. Okay, but if you compare here, this is the dividend can be less than the divisor. No other bits are available in the dividend to copy. So this is the remainder. And the values that can be produced after the each subtraction can be called as partial remainders. So this is not the actual remainder. In the successive steps, we can at the end of the division we can get the remainder. What is the middle products that can be available? Those terms can be treated as the partial remainder. In this way, the binary division operation can consist of majorly the comparison, the subtraction and shift right operation. Now we will consider one example. So here 101010 is the dividend and we have to take in 110. First the 3 bits can be considered and whether they are greater than or equal with the dividend, the comparison can be made. So here 101. So here the value can be less. So extra bit can be considered here and compared with the divisor. So with this bit while comparison, the dividend value can be greater. A 1 can be copied in the quotient and the the divisor value can be copied here and perform the subtraction. So here after subtraction you can get 110, which is exactly equivalent to the divisor. A 1 can be written and here 110 again copied. The remainder can be 0. So in this way the divisor and dividend value can be compared. If it all the dividend contains the greater value, a 1 can be written in the quotient. Otherwise, a 0 can be written in the quotient. Take into one more example. Here this is the divisor and the dividend, and this is the divisor. And first taken the 3 bits of taking from the MSB. The 3 bits can be considered. So the dividend value can be greater. So 1 can be written in the quotient and the divisor can be copied here and made the subtraction. Later on, the next bit can be appended to the partial remainder. But here, it won't be greater than the divisor. So, the subtraction cannot be go. So, again, one more bit can be appended to the partial remainder by writing 0 at the quotient. And while comparing, the dividend value can be less than the divisor. Again, one more 0 can be written appended in the quotient. So after considering the 4 bits, the dividend value can be greater. So a 1 can be copied in the quotient and the divisor value can be copied here and compare the made the subtraction. So here after subtracting the value, the next bit can be appended and here the dividend value can be greater than the divisor. A 1 can be written and the divisor value can be copied and the subtraction operation can be performed and the remainder can be the 1. Next bit can be appended 10. No other further bits are there. So here this is the remainder of the this division. What is the circuitry, electronic circuitry that can help the division process? In the hardware implementation of division, the dividend or partial remainder is shifted to the left, then shifting the divisor to the right. Thus, the two numbers are left in the required relative position. Subtraction is achieved by adding its 2's complement of the divisor to the dividend. So, subtraction can be performed with the help of 2's complement addition. The information about relative magnitudes, whether the dividend set is greater than divisor, is available from the end carry. So here, in order to perform the binary division, the hardware circuitry is divisor B is stored in a register, dividend A and the partial remainder can be stored in the A register as well as the quotient is stored in the Q register. And here the ALU can perform the operations and here during subtraction can be performed with the 2's complement addition. If extra carry is generated, that can be stored in the E. So in order to perform the shift operation, shift counter can be used. So this is the electronic circuitry required to perform the binary division. The divisor, the dividend and quotient are all n-bit registers. The dividend is extended with a 1-bit E for evaluating relative magnitude. E bit and the register A and Q are considered together as EAQ register. So while performing the shift operation, these 3 flip-flop E, register A, Q, both 3 can be considered. So EAQ, we have to perform the shift operation. As shift left happens, the dividend set becomes available in A and quotient gets collected into Q. The shift counter keeps track of the number of bits in the dividend, which is generally equal to the word size. The operation is repeated until all bits of the dividend are evaluated. So in this way, the hardware can be supported to perform the binary division. In the division, there are two categories of algorithms. One is the restoring division algorithm. Second category is non-restoring division algorithm. We will look into one after another. The first we will consider the restoring division algorithm. In the restoring division is a method wherein by default, without identifying the magnitude of the dividend set, the divisor is subtracted. That what is the term that is produced after subtraction is generally referred as trial subtraction. If the result of trial subtraction is positive, then the quotient is marked as 0 and the subtraction becomes the desired step. However, if the trial subtraction result is negative, then this becomes the undesired steps. So, the step is reverted or restored by adding again the divisor. So here in this step we performed the subtraction. If the result is negative, then again we are adding the divisor, so in order to restore its previous value. So subsequently the quotient is marked as 0. For this reason, this method is called as restoring division method. So what is the flowchart of this restoring division algorithm? Dividend is stored in AQ register, divisor is stored in B register, sequence counter can store how many number of bits are there in the dividend, and E is initially stored the 0 value. Next, perform the shift left EAQ on the 3 flip-flop E and AQ registers. The shift left operation can be performed and A minus B value can be stored in E and A. And we have to check the trial subtraction value is positive or negative. How can you decide is based on the E flip-flop value. If E value can be is equal to 1, then the quotient term can be 1 and sequence counter can be incremented, and if there is no bits in the dividend, the division process can be stopped. But if at all the trial subtraction is 0, again we have to restore the value of the dividend. So EA is A plus B. Whatever you performed here, the subtraction, again previous value can be restored by performing the addition operation by posting a 0 in the Q0 bit. So this is in this way the value can be restored. That's why this method is called restore division algorithm. So let us consider with an example how the restore division can work. So we have to take the value 194 example as 194 divided by 10. So here 194 binary value, 10 binary value in the 8-bit can be considered. So internal values in the B register, the dividend has to be stored. So initially in the B register, the divisor value can be stored. A is equating with all zeros. Q can be the value, and here the 2's complement of 10 can be taken. Why? Because the subtraction can be performed with the 2's complement of addition. So first we have to perform the shift left EAQ. So E value, A value, Q value can be considered and a shift left operation can be performed. In the second step, subtract the A minus B operation can be performed and the result is stored in E and A. And we compare the E value whether it is 0 or 1. So from this step we can get the trial subtracted value and we can check whether this subtracted term is positive or negative with the help of E flip-flop. So if at all E is equal to 0, then there is the division process can be carried out by placing the quotient as 1. So in this way, the successive comparison, shifting, subtraction and successive comparisons can be made, and depending upon the trial subtraction value positive or negative, the restore operation can be performed when the trial subtraction value is negative. In this way, the restore division algorithm can be worked. So this process can be continued until no other bits can be evaluated in the dividend. So the sequence counter can reach the number of bits present in the dividend. These steps can be performed. The shift left operation, subtraction operation, comparing E whether the subtracted term trial subtraction is positive or negative. So this way the steps can be repeated until the number of bits in the SC counter can be equal to the number of bits in the dividend. The second way of division is non-restoring division. The non-restoring division is expected to eliminate the 50% overhead due to restoration. In restoring algorithm, on finding the A minus B to be negative, restoration was be done by adding the B. Okay. So if you A minus B plus B is equal to A, the left shift was be done in subsequent iteration. So A minus B will be found out. So this is the working of the restore algorithm with the example just now we discussed. But in case of non-restoring algorithm, on finding the A minus B to be negative, B is not added right then. Instead, it proceed with the shift left. Then in the next time around the loop B is added, the correction is applied at the stage of final remainder. So here we cannot directly add after identifying trial subtraction value is negative. So here the shift left operation can be performed and next time around the loop B is added so that the value can be restored. So this is the flow chart of non-restoring division algorithm. The dividend is placed in the queue, divisor is in B, a sequence counter can be equated to number of bits in the dividend, E equal to 0, A equal to 0. First shift left operation can be performed on EAQ, and here checking of the trial subtraction value whether it is positive or negative. In case of positive, A plus B, and again we have to check the E value, and if it all negative, A minus B can be performed and again checking the E value. If it all E is 1, the positive value, then Q can be 0, SE can be decremented. If it all the negative one, Q naught can be the 1. So this way the sequence counter value can be checked whether it is reached to the number of bits or not. So here each and every time again the E value can be compared here, and here if it all it can be the positive number, then A plus B again restoring value can be performed here. So in this way, right now, after observing here in the trial subtraction whether it is having positive or negative, immediately there itself it is not adding it. It is shifting, and in the loop value it can again check. There the correction can be made in the non-restoring algorithm. So in the non-restoring algorithm, the actual process is initialize the E and A to 0, load dividend to Q, divisor in B, load shift register with word size n value. Shift left EAQ by 1. If E value is 0, find A minus B, else find A plus B. And if the new E value is 0, set to quotient 1, else 0. Reduce SC shift counter by 1. Repeat steps 2 to 5 until shift counter is greater than 0. Correction is required for the final remainder if E value is 1, A is negative. Do the correction by using the addition operation. So here the restoring can be done at the final result. The final remainder in the A register, final quotient in the Q register. So this is the difference between restoring algorithm and non-restoring division algorithm. Now consider one example how the non-restoring division algorithm can be worked. So here we have to take the 19490 and here 194 value, dividend value stored in Q and the divisor value can be stored in B. In order to perform the subtraction, 2's complement of 10 can be considered. So what are the steps generally that can be made in each loop step is, each iteration is, first shift left the EAQ and check whether E is 0. Okay, if E is 0, subtraction can be performed. If E is equal to 1, then Q0 can be 0. So like this, these steps can be repeated. But at the last, after counter can be exhausted to the number of bits, then the final remainder, the plus operation can be performed in order to restore the actual value. If at all it is a negative case. This way, the non-restoring division algorithm can be worked. So each step, each iteration, these steps can be repeated until SE can reach the number of bits of the dividend. So here there is a problem of divide overflow. An overflow is a situation that the resulting number is not larger than that can be represented in a word. The registers can be is of fixed size. If at all an overflow is generated due to arithmetic operation, it is very complicated to store these overflow bit. Thus, divide overflow occurs when the divisor value is 0. Any dividend being divided by 0 result in divide overflow. So it can also be happen if the resulting quotient is too large to be fit in the variable defined in the program. So divide overflow generates an exception in the hardware. So the size of the register cannot accommodate this overflow bit. So it raises an exception in the hardware. That's why before further going into the division either by restoring or non-restoring method, first check whether the divide overflow can occur or not. So here after subtraction can be performed with the 2's complement addition, the E value can be checked and depending upon the E value is 1, the divide overflow can be the 1. Extra bit is generated during the addition operation. So the divide overflow can be set 1 in order to end and avoid the exception in the hardware. If at all it is 0, we can proceed with either the restoring or non-restoring division algorithm that we discussed earlier. So that is the way how the binary division can be performed. Now we can discuss about how the decimal arithmetic unit can be worked. The decimal arithmetic operations refer to a digital function that does decimal micro operations. So the user of a computer prepares data with decimal numbers and receives result in decimal form. So here the input data can be in the decimal form and the output data can also be in the decimal form. A single stage decimal arithmetic unit consists of 9 binary input variables and 5 binary output variables. Since a minimum of 4 bits is required to represent each coded decimal digit, each stage must have 4 input for a added digit, 4 input for the added digit and an input carry. So in case of addition, to hold the added and added and additionally the circuit can support the input carry. The output includes 4 terminals for the sum digit and 1 for output carry. So this is the decimal arithmetic unit. So BCD 9 complementer can be used, BCD adder can be used. Here the AGEND and addend can be supported, can be given as input and in a decimal form, and the sum and carry can also be received in the form of decimal form. How parallelly the addition can be performed with the decimal arithmetic unit. Consider an example 624 plus 879. So the unit plus is 9 and 4. Parallelly these digits has to be added. So the first BCD adder can receive the 9 binary value and the 4 binary value. What is the sum that can be produced here is the 3. Okay, if it all carry is there, that can be feed forwarded to the next BCD adder. So all these BCD adders can be connected in a cascade fashion. The second, in the 10th place, what are the values are there? Those can be carried out with the next BCD adder. So 7, next 2, both can be added by using this BCD adder. So the result can be the zeros. So like this way, each digit from the AGEND and addend registers can be considered the corresponding digits, and they can has to produce the sum, and the carry can be feed forwarded to the next BCD adder. And another way of performing this digit serial bit parallel decimal addition. So here BCD adder, and what is the AGEND data is given, and what is the addend data has to be stored. So those can be given in a parallel to the BCD adder, and sum is stored in a vector. So the carry can be given in a feed forward fashion to a BCD adder. So digits can be supplied serially, bit parallel decimal addition can be performed, and sum is stored in the corresponding vector position. Next, another way is all serial decimal addition. The AGEND register values can be taken to a full adder, and sum can be stored in the sum vector, and carry can be feed forward with a correction. So like this, the serial and parallel, the decimal arithmetic unit can be used for addition of corresponding bit positions, and the input can be given as here decimal, which can be represented by using at least 4-bit binary number, and the circuit BCD adder can perform the addition and produces the sum and carry. In this way, the decimal arithmetic unit can perform the addition either serially or parallelly. So in this video, I discussed about what is binary division algorithm, the two methods restoring and not restoring, and how the decimal arithmetic unit can perform the addition operation. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.